Hi, this is Charlie. Welcome to our next lecture. Let me share my screen and we can get started, okay? Share my screen. Hopefully everyone's have had a great week last week. I think most of the assignments were submitted. I have a few I still have to grade. Uh, but let me pull this up here. Okay, we're on Module 2, Data Manipulation. And I would say that this is the most difficult lecture, the most difficult homework, okay? If you get past this, I'm not saying the rest of the course is easy, but it's students find the other topics easier to understand, okay? So I have to be honest about that. So you got to read chapter 2 in the book. Here's some optional watch, some things you can watch optionally on computer architecture. There'll be a quiz. There's a quiz basically after every lecture. And there's usually an assignment. There's assignment number 2, and there's usually a discussion, okay? So let me get to the uh the lecture. Here it is. Okay, let's go to the beginning. Okay, there's the book, and we're going to use the book tonight as well. I'm going to go over one of the problems in the homework and how to use the book. And the book is free online, so we have a link to it in our course. So, data manipulation, chapter 2. Hopefully, hopefully, computer architecture is a review for you, or it's easy to understand. Then we're going to go to machine language. That's probably something new. Program execution, arithmetic logic, communicating with other devices, programming, data manipulation, and other architectures. Okay, so uh, the machine language, I think, is something that most of the students struggle with if they struggle with and any part of this as well as with the program execution. But I hopefully I can explain it thoroughly enough that you can understand it, and I will do one of the problems in the homework to get you started. Okay, the computer architecture, I think we all kind of understand this a little bit. There's a central processing unit, right? It consists of the arithmetic logic unit, the control unit, and the registry units, right? General purpose registers and special purpose registers. Then there's a bus, and then there's main memory. The bus is needed to transfer from the main memory to the CPU, right? Data. So via bus, and this is what I was talking about here. So you have your CPU, the registers, and a bus to main memory. So the when data is requested from main memory, it travels the bus and it's put in the registers, and then the arithmetic unit and the control units take over. Okay. And if you notice the bus, there's multiple lines, right? Uh, so that we can so we can try to be as efficient as possible. It's just not one line there, Representative. That's the reason for it. So you could split up the large amount of data and send it across, split up between the lines and send that data across. And that's why it's just not one line. Stored program concept. A program can be encoded as bit patterns and stored in main memory okay, so everything is bits, right? From there, the control unit can extract, decode, and execute instructions. Okay. So the control unit right here executes the instructions. Instead of rewiring the CPU, the program could be altered by changing the contents of main memory, right? We don't want to rewire the CPU. Machine language, machine instruction, right? There's an instruction code as a bit pattern recognized by the CPU, right? So the machine instruction is based upon the CPU architecture, the architecture of the machine. Machine language, the set of all instructions recognized by a machine. Okay. Machine language philosophies, there's two of them. Reduced instruction set computing, RISC. Few simple, efficient, and fast instructions. Um, these would be examples of your Power PC from Apple, IBM, Motorola, and ARM. I know that I'm using a laptop and I use computers that are mostly CIS, complex instruction set computing, many convenient and powerful instructions, and that an example is Intel, right? So most most of most of us I think are on Intel, CIS set. Machine instruction types. So you have data transfer, copy data from one location to another, like load and store. And by the way, we're going to go over examples of this. It's maybe a little confusing right now. We're going to go over some specific examples, and the homework problem I'm going to go over deals with this as well. Arithmetic logic operations on bit pads, right? What can you do with bits? You can add them. We noticed from the first homework, you can add bits, subtract them, you can shift them, rotate them, right? And then there's the control, direct execution of program. Maybe you jump somewhere in your program, you branch somewhere. So uh, that controls the execution of the program. Maybe you've written a program, it goes to a certain line in the program. If X equals 1, then go to subroutine 2. If X equals 3, go to subroutine 3, and so forth, right? That's an example. Adding values stored in memory. Okay, so let's see here. Okay, so I can fit it on the screen. So this is important. So the step one, get one of the values to be added from memory and place it into a register. Okay. Get the other value to be added from memory and place it in another register. Okay, so we're going to add values and stored in memory. We're going to take the values and place them in the registers. We'll register in another register. Then activate the addition circuitry with the registers used in steps 1 and 2 as inputs, and another register designated to hold the result. So 3 registers are used. Register 1, let's say, stores the first value. Register 2 stores the second value. The addition of register 1 and register 2 is stored in the third register, right? And then you store the result in memory. Okay? Adding values stored in memory. Okay, load a register with it. So this was like an English, just a pseudocode description of what to be done. And now here's more like machine code. Step one, load a register with the value from memory. So it's actually a load command. And then load another value from memory. There's another, so that's the second load command. If this second value is 0, jump to step 6. So here's the jump. If the second value is 0, okay, so we're doing division, so we can't divide by 0. And step 6 says stop. Okay, divide the contents of the first register by the second register and read the result in the third register. Again, using multiple registers. Store the contents of the third register in memory. Can you stop? Okay, in the book, and we'll come to it when we do the homework example. I'll go into the book in more detail in Appendix C. But here's the architecture of Vol. Vol is a make believe machine, okay? But it's pretty good. It's a pretty good representation of how it actually works in a real computer. Okay, so you have your central processing unit. You have if you see here on the left, the registers numbered sequentially. And then there's something called an program counter. That's in the central processing unit instruction register. Okay. As you see the bus, and here's your main memory. Again, uh, sequentially numbered. Okay. So parts of the machine instruction. Opcode specifies which operation to execute. Operand gives more detailed information about the operation, okay? Interpretation of operand depends upon the opcode. So the composition of a vol instruction, there'll be an opcode. The opcode comes first on the left. In this case, it's 3. And here's the operand. And that's broken out into, if you notice, 4 bits. It's the vol instructions are 16 bits or 2 bytes, okay, in total. That's very important to understand when with the registers, and we'll get to it in more detail, okay? Decoding the instruction. Opcode B means to change the value of the program counter. This is all in Appendix C. Uh, and then the part of the operand identifies the register being compared to register 0 when it's 2, hex 2. And then this part of the operand is the address to be placed in the program counter. Okay, an encoded version of the instructions in figure 2.2. It's a little confusing here. 2.2 was this figure adding values stored in memory, okay? That we covered. So let's go down here. We covered that, covered this. Okay, and encoded. Okay, so here's encoded hex 1 56C loads register 5 with the bit pattern found in the memory cell at address 6C. Okay, that's the machine code. Then load register 6 with the bit pattern found in memory cell address 6D. Okay, so we took address 6C, 6D, and load it. And then add the contents of the register 5 and 6. So here's 5 and 6. And they were 2's complement representation and leave the result in 0 right here, that hex. Okay. And then the next machine code, hex 36E, store the contents of register 0 in the memory cell at address 6E and halt. Now, if this seems a little confusing, just hold on. We're going to get to a much better explanation, and I'm going to do an example, and hopefully you don't find it as confusing, because I know I'd be a little confused right now myself. I will go to the appendices and do an example, for the homework example, and it should clear it up a little bit, okay? And then this will make much more sense to you. Program execution controlled by 2 special purpose registers, the instruction register. So the instruction register holds the current instruction, and the program counter holds the address of the next instruction. This is important to understand, okay? This is, you need to understand this. Machine cycle, repeat these 3 times. Fetch, decode, execute. Repeat these 3 steps, okay? And so here's the machine cycle. This is important to know. First thing, you're going to retrieve the next instruction, okay, as indicated by the program counter, and then increment the program counter. Then you decode the bit pattern in the instruction, and then perform the the action, right? Perform the action in the instruction. And then, so it's cyclical. You fetch, decode, execute, fetch, decode, and execute. Okay, here's decode the instruction B258. So again, the first, it's split up. Opcode B means to change the value of the program counter if the contents of the indicated register is the same as that in 0. 2, party identifies the register to be compared to register 0. And then this part of the operand is the address to be placed in the program counter. Okay. Okay. The program from figure 2.7 stored in main memory ready for execution. So we have a program counter, right? And we have an instruction register not set yet. And as you see, the registers on the left do not contain any information. And here's the program stored in main memory, right? So uh, for the purposes of this course, our program will be contained in main memory. This is a high-level course, computer architecture, operating systems, and all that fun stuff. They could require maybe I've seen, like, for example, computer architecture. I've seen two different distinct courses offered at a university for computer architecture 1 and computer architecture 2. And so for the purpose of this course, it's just in main memory. Okay? Let's move on to the next one. Perform the fetch step. So the program counter is at hex A0, right? And then the fetch counter is at 156C. The instruction register, okay? Very important here. If you notice, it had to take two addresses to form the instruction register because, again, vol is a 2-byte machine and the addresses are 1 byte. So you have to combine both of them, uh, two of them. You can't just do one. And that's a mistake that a lot of students are making on the homework problem. Uh, they do not increment the program counter properly because they're going down address by address by address. So they're going hex A0, hex A1, hex A2, hex A3. No, uh, your first program counter will be hex A0, and the next program counter will be at hex A2. Okay? Uh, because you have to consider that it's a 2-byte machine, and the registries are the memory addresses are only 1 byte. At the beginning of the fetch step, the instruction star address hex A0 is retrieved from memory and placed in the instruction register. Okay, that might be a mistake. Okay, instruction register. Program counter. Okay, but two. Then the program counter is incremented so it points to the next instruction. You see, the next instruction, the program counter, the next instruction is at what I was talking about is hex A2, not hex A1. Okay. Arithmetic logic instructions. Because you have and, or, XOR. We learned this in the last lecture of with bits, and we learned about the circuits and all that fun stuff, right? Often used to mask an operand. Okay. Rotation and shift bits. Maybe circular shift, you could shift them to the right, shift them to the left. Uh, you see this in algorithms that are using encryption. Okay. And there are arithmetic operations, add, subtract, multiply, divide, right? Two's complement versus floating point, right? We would need that in a machine, right? If we couldn't do arithmetic operations, we couldn't do ands or do any logical operations. What good would it be, honestly? Okay, rotating the bit pattern hex 65 1 bit to the right. This is an example of rotating it to the right. We take the bit that's to the right, move it to the left, and shift everything down, right? That's what was done here, right? Okay. Communicating with other devices. A controller handles communication between the computer and other devices, right? Yeah, USB, HDMI, a port. The port which a device connects to a computer. You can think of a port as a port, like a port, in the ocean, you have a port where ships dock. We need those ports because you could have multiple devices, and each device could have its own protocol or way of communicating. Therefore, we can't have that mixed, right? That information mixed. So applications run and listen on have their own unique ports. so that they can communicate properly. Memory mapped I/O. Devices appear to the CPU as though they were memory locations, right? It's just the way that they work. They map them to I/O input output. Here's an example, okay? Controllers attached to a machine's bus. Here's the bus, here's the CPU, here's the main memory, here's the controller, and here's a DVD drive, I guess we'll say, and here's the mouse, okay? And here's the screen. I don't know what that represents, some type of card, a network card maybe. So there are different controllers to different devices, right? And they're all listening on different ports. Here's a conceptual representation of memory mapped I/O. The CPU, the bus, the main memory, controller, peripheral device, which is pretty much the same as the previous document. Communicating with other devices. Direct memory access. Main memory access by controller over the bus. There's a von Neumann, they call it the von Neumann bottleneck. Occurs when the CPU and controllers compete for bus access, right? There's a bottleneck. Handshaking, that's a common uh, way protocols work, is the process of coordinate the transfer of data between computer and the peripheral device. So example of handshaking could be, let's say it's the device is a printer, and you're going to print a Word document. There's a handshake that says the computer go out and says, "Okay, are you ready to print the printer?" The printer says, "Yes." Okay, going to send the data. Okay, right now, you also get an error. Let's say if it says, "Okay, are you a printer? Are you online? Are you ready to print?" It says no. Then that's when you get the error. So that's what handshaking is all about, right? Communicating with other devices, popular communication media, right? So there's parallel communication. Of course, we want to try to do things in parallel, right? Because it's faster. So several signals transfer the same type, each on a separate line, right? That's what I was talking about the bus. Why the bus? You have multiple lines in the pictorials for the bus. Serial communication signals are transferred one after the other over a single line, like USB or FireWire. Okay. Data communication rates. So this is when they talk about, we're always concerned about how fast is our data being transferred, right? So BPS is bits per second, kilobits per second, 1,000 bits per second, megabits per second is a million, and gigabits is a billion, right? That's the bandwidth that we're talking about. These are the rates. Program data manipulation. Okay. Program languages shields us from the details of the machine. Okay, so that's, when it comes to the programming languages, back in the day, many years ago, when the programming languages weren't developed, it was a pain in the neck to do the machine code. Lots of uh, machine lines that you would have to, lots of code that you'd have to produce for the machine code. But now, let's say you have a language like Python, only a few lines of Python produces lots of machine code. So you're working at a higher level, you can get more done, you're much more efficient, right? Program does not need to know if the processor is RISC or sys, right? You're independent of the underlying hardware. Assigning variables surely involves load, store, and move operate opcodes. Bitwise problems as Python code. So you can do these logical operands inside the code. Okay, we're not going to program in Python in this course. But if you're a Python programmer, you want to try these examples, go ahead. I think it'd be good to just experiment with Python a little bit. Control statements, right? If water temperature is greater than 40, print bath water too hot. And of course, there are while statements. While n is less than 10, it's just printing out numbers. But behind the scenes, the actual machine code, or I'm going to call it assembly code, it's hundreds of lines of that, where you only have a couple lines here. So function, there are functions, a name of series of operands that should be performed on the given parameter or parameters, right? So you logically, when you write a program, you might group them into functions. Other languages may call it procedures. Other language object-oriented methods, right? So you group them together, what makes sense. So here's an example of x equals, so they assign a value x, y, and z. You take they take a max and it prints it out. Okay. Argument value, right? So a value plugged into a parameter, fruitful functions return a value, right? Void functions or procedures not return a value. Here's an example. There's two sides, an A and a B. Hypotenuse, A squared plus B squared equals C squared. I remember that from way back in the day. And then you print out the hypotenuse. Okay. Input output calculates the hypotenuse of a right triangle. So this is definitely Python. We're importing the math library. So we get a side we're asking what's the length to A, what's the length to B, and then again we uh, print the hypotenuse. Now you're not going to be questioned on any of this. I think this is just giving you background of some programming. Import math, right? Total seconds. So here's a function that's total seconds. It takes the minutes and multiplies them by 60 to return and the seconds. So divide time, 360 divided by time, right? How many, the speed, how many seconds divided by the time. Okay. And here's a program uh, for pace of mileage. You can go read that on your own. And here's the output right to the table. Okay. Other architectures. Technologies to increase throughput, pipelining, okay? Overlap steps of the machine cycle. Parallel processing, use multiple processes simultaneously. SIST, SISD, single instruction, single data. MIMD, and that has no parallel processing. Multiple instruction, multiple data. Different programs, different data. SIMD, single instruction, multiple data. Same program, the data. So that's it for the lecture. And again, I think when you talk about architectures, what we're trying to do is we're trying to process the information as quickly as possible. We're trying to get our programs to run as quickly as possible, and that's why they come up with these architectures. And so what I like to do is I like to go into the book and let's go into the book. Okay, let's use the latest edition. And let's go, let me download this. Uh, where's the download button here? I should have, maybe I can download this. Okay, PDF document. It's nice, it's a PDF document. I would suggest that you download this and save this book. It's a pretty good book. You're getting it for free. I would download this. Okay, so we have Appendix C. Where is Appendix C? Let me go to Appendix C. Oh, they were talking about the Gates data we could recognize. Okay, so here I am here. This is what we've been talking about. Okay, so again, let's read this paragraph. Each file machine instruction is 2 bytes long, 16 bits. The first 4 bits represent the opcode. The last 12 bits make up the operand field, right? The table that follows lists the instructions in hexadecimal routine with a short description of each. The letters R, S, and T are used in place of hexadecimal digits in those fields, representing register identifiers and values, right? depending upon the instruction. The letters X and Y are used in lieu of hexadecimal digits. So let's go to one. Let's look at this first one. This is the opcode is 0 hex 1, operand RXY. It'll load the register R with the bit pattern found in the memory cell XY. And here's an example. So I want to copy this. I'm going to put it in Notepad. And we're going to just study this a little bit so that we understand this. Well, this is for the homework. Let's duplicate this tab. Okay. So they want to take an example here. Here's how I would go about working on these problems and understanding this. So you have 0 hex 1. That's load the register. So 0 hex 1 says load. This is load. At address 083 to be placed in register 4. So this is X. And this is Y. Okay? So cause the contents load the register R with the bit pattern found in the memory cells whose address is XY. Oh, okay. This is the register, register 4, and this is XY. So RXY, okay? So when you do your homework, I want you to go to this level to explain this. So this is going to load and register 4A3. So what I would put that down here, register 4 equals XY, which equals A3, okay? Let's try another one, maybe a more complicated one, and then we can try the homework. Uh, so we did RXY. Let's see here. Maybe we'll do store. Let's do 03. I don't know. Let's pick something that's easy for me to copy out of. Oh, this drives me crazy sometimes. Let's pick something that's easy to copy out of. Okay, I'll see how this one goes. I can't, let's see what this looks like here. So that's okay. I got extra ones here. Load 5. It's just hard to copy out of this. Okay, so this should be it. RX5, load the register R with the bad and bat. So this one is, we're gonna load the register R with the bit pattern XY. So this is 2. So the first bits is 2. Okay, so let's write this example down and go over this again. So if you were to take this, right? So this is how it always works. Split this out, right? So hex 2. Now if you go back into here, no, where is it? So 2, we're doing 2, okay, copy. So we're doing this one. So opcode is 2. Load the register R, so RXY. Okay, so this is 2. You look up the opcode 2. So now what we're going to do is, so 0 hex 2 are 0 to a X and Y. So it says load the bit pattern, load the register R So this is the register, right? Because X, it says here RXY. So this is RX, right? So this is the load, because it's hex 2, RX. Y. Now, so load the register R with the bit pattern found in XY. So register 0 equals the value. Okay, so I want to go back up to this first example. We did load the register R with the bit pattern found in the memory cell. Okay, equals the contents. How do this? It's the memory cell at A3. So do this. At the contents, whatever is at A3, we want the contents at A3. Okay? I don't know what that is. Okay, so it's not A3, it's the see, that's why you got to be careful when you read this. Load the register with the bit pattern found in the memory cell whose address is X3. So you could say contents, you could say bits. So I understand that you're trying to, right? So I understand you're saying bits, or you could also do this if you want to. Some they do this is I understand that I reverse malware a lot, and so when I'm looking at the assembly code, if I see this, just the brackets, that's telling me the contents of A3. Okay, so I want the contents A3. This is not saying that. Okay, so load the register R with the bit pattern XY, which is different. Okay. Okay, so you put some bits in XY, right? So that's what you'd want to say here. Bits in XY. This takes a little bit. Okay, so now this is a little different. In O2, it's asking you load register R with a bit pattern XY. So, and that equals, so it's good that we picked this one. That equals A3. Okay, you see the difference? The first one is you're taking whatever at the address X3, give me the contents, whatever that is. This at register 0 now, at the register 0, we're just taking A3, not what's inside of A3. Okay? So uh so there are quite a bit of operands. Okay, we could store bit patterns. There's a store, there's a move. If you notice here, the move doesn't have an XY. It has an RS, right? So maybe we'll do one of those too, one that doesn't have an XY. Uh, RST, add the bit patterns found in register NT as though they were two complement representations and leave the result in register R. Let's see how this one of these kind. So there's an add, a move, another add, six is add the bit patterns in registers S and T. So you get the idea. You use this appendix for all the different app codes. You find the app code and then you interpret what it's asking you for. Now, maybe there's one. How about this one? Okay. Okay. If anybody has a trick on how to copy just certain things you want out of this PDF, you let me know because I cannot get a good copy of this. Probably the best thing would do is do this. Okay, here's what I could do. I'll copy the whole complete thing. I don't know why I didn't think of this. Copy this in here, and then we could pick it out, right? So it's a little trick here to copy it out. let's see what we get here. Well, not really not too bad. Uh, so let's go up to one of these. We'll pull it out. Well, this is actually very difficult. It's not it doesn't copy right. Uh, Maybe it's a good idea to convert it to Word first so that you can copy out. So generally speaking, you get the idea, hopefully. Here, we'll try this one. This is easy to copy. What does this one do? Okay, let's work on this one. Let's work on this one. Okay. So jump to the instruction located in memory cell. So if the operand it starts with B, 0 hex B. Okay. So let's copy this. So here's the example. Let's see how we do on this one. See, so, and I would recommend to go through each one of these, make sure you understand it fully before doing the homework. So again, I space it out, and this is RXY. So let me space this out. Right, so again, this would be the register, X and Y. And so this says jump to the instruction at memory cell at address XY. If the bit pattern in R is equal to the bit pattern in register number 0. Okay, so if the bit pattern, so if register 4, so here's our if thing, right? So if register 4, so they're saying it's equal to the bit pattern found in a registered number 0. I'm sorry, I typed that wrong. If register 4 equals register 0, so if we have 4 equals 0, so, okay, then jump. Okay, we could just say jump here. Jump. Memory cell at address XY. Jump to 3C. Here we could do this, 0 hex 3C. Okay. So that's what this example translating it, that's what it is. So in the homework you will have, there's going to be a question they're going to ask, kind of do the reversing. They give you you have to say in English what it does, right? So that's why I say provide what it does. So that's why it's good to go through each one of these in the appendices and make sure you understand it, write it out. Okay. So now I want to go to the homework. So let's review the homework. Chapter 2, homework. Suppose machine language designer opcode 4 bits, how many different bits? That I think you could handle no problem. Suppose three values x and y stored in the machine's memory describe the sequence of events. We've covered this. This is moving x, y, and z into their own registers and having another register to do the sum or do the calculation. They're asking for 2x plus y plus z and 2 y z, right? So the following are instructions with an evolved machine. Translate them into the English. That's what I was talking about. So we could try one of these. Okay, let's try one of these, just one of them, and that's what I was talking about. So here's what I would do. Let me duplicate. Actually, 1 second here. A stupid thing. So here's what we could do. Okay, so I want to get rid of this. Okay. So we have this. Okay. So what I always do is I would start with 0 hex 7 1 2 3. Okay. So now you have to go into we want to go into dependencies. We have to find 7. So we find 7 here. Uh, okay. Not bad. I got that copied in there. Okay. So let's take the description here. I like to write, and I want you to show this work, okay? So try to do it kind of like I'm doing because I like to read your logic and how you're doing it. If you just provide the answers, I don't like that. I want you to show the work, okay? So are the bit pattern registers, so what did I miss here that I copied out? Or. So this is or. Or the bit pattern registers S and T and place the result in R. So this is, so here we have RST. So this is RST, okay? R S T. So now what you can do. So now so now if you do this, you can copy this, right? Or the bit font in registers S2, registers 2. So now you can substitute it. 2. Of course, this is, of course, nothing. 2 and 3, and place the result in register R, which is 1. Okay, so there's a simple way. If you do it this way I'm showing you, and you write it out, and you put with the operands and the operand and the operands under it, you write out under it, and then you copy the description, you now just have to substitute the variables, right? And so that's what that does. So that's what that did do for the homework. So those problems, I think, if you do it this way, shouldn't have an issue. Okay. Suppose, okay, this is the big one. I think this is the important one to understand. And I want to go through, I'm probably going to go through most of this because for number 4, because a lot of students struggle with this. And I want you to learn, I want you to work on it. So do your own work on this. Refer back to this, well, how I'm going to do this problem. Uh, and then you can, then you'll understand it. And then problem number 5. Okay, problem number 6 is the same exact problem. Basically, they're asking you to do the machine cycle. So if I do number 4, I'm not going to do number 6. I'll leave it up to you to do number 6. So I put this in. I put this in. Where is this thing? I put it in. Not here. Here. No. Uh, okay, we'll just copy it again. So let's do this. This is easy to copy. Getting too many notepads open. Okay, so here we go. So remember, Voltaire is 2-byte machine. So the program counter is going to start at this first line, okay? I'm going to put the program counter here. Program counter is here. We're going to start this line. So what I would do is, it's very simple. Enter, enter. Split them. Because uh, it's 2 bytes. So the first instruction is instruction 1. So maybe you do something like this. Instruction I1. I don't know. Instruction one is 0 hex 2, 2, 1, 1. So you had to combine both. A memory location is 0, 0 and 0, 1. And then the program counter will come down to here, right? Right? So this is the first instruction. And then the program counter would get set here. So that's our next instruction, okay? So now what I would do is for the first instruction, again, I would space this out. Okay, so we're going to go look for 2. We're going to look for 2 in the appendices. Here in this chart. This is this one. No. So it's RXY 2. Okay, so I would put this here. Okay, it makes it easier. So you just put this. So this is R X Y. So what does it say? Load the register R with the bit pattern XY. So register 2. Now these are memory locations. These are not registers. So register 2 equals bit pattern XY equals the XY, which equals 1, 1. Okay? So I got the first register 2, right? So that's what they're saying. That's the register. Their example here, they're using a 0. Here we have register 2. So register 2 equals XY, which equals 11. 1, 1, not 11. Bit pattern 1, 1. Okay? You could always do this. It's kind of a good idea. So you know it's not 11. Okay. Now instruction 2. We're on instruction 2. Instruction 2 has 0 hex 3, 2, 0, 2. And of course, now the program counter that's the instruction. The program counter will move down to here, and this will be our last. We'll eventually get to here. So I don't know. Uh, you can do that on your own as you're going through. Phase it out, move it over. Ah, phase it out, move it over. You can do this as you're doing it, or you could document it where the program counter is at, right? So anyway, so instruction 2 is that. So now for instruction 2, uh, that's how you do that. Instruction 2, why is this? Okay, so I would break this out more. Again, I'm very disciplined at this. Okay, and so what I do here is now I'm going to go into the find 3. And it's very important. I would not make sure. So it's RXY again. Uh, do not rush through this. Make sure that you read the description once or twice so that you don't get confused between contents and registers and bits, right? That's where you could screw up a little bit. So you got to take your time. So store the bit pattern found in register R. So this is X and Y. So this will store the bit pattern in register in the memory cell whose address is XY. memory cell, who's that? So R register 2 equals, again, I'm going to use this, the contents of XY, right? Which equals the contents of 0, 2 in memory, the memory of 0, 2, which equals right here. Here's our memory 0, 2, right? Okay, make sure I got that right. So load the register R with the bit, okay, load, store the bit pattern found in register R in the main memory whose address is XY. Store the bit pattern found in register R, R2. Oh, okay. See, I read that wrong too. You see, this is why you got to read this. This is what it's really saying, okay? That's why you got to read over to store the bit pattern found in register R. So the contents of register 2, which equals, that's why they did this, is this, right? Contents of register 2 equals store the found in the memory cell whose address is XY, right? Equals, so register 2, the contents of the register 2, store the bit pattern for register 2 in the memory cell whose address is XY, 0, 2. So the contents of that equals store the bit pattern found in register R in the memory cell whose address is XY, contents of XY, which is 2, right? So basically that's it, right? So, because X2, we register 2. Do I know what I'm doing here? One second, let me just get, some of this is confusing. Store the bit pattern found in register R in the memory cell. Store the bit pattern found in register R, register 2. Register 2 has 11, right? Store the bit pattern found in register R. Register R equals, okay, no, I'm wrong. Okay, this is it. I got it now. Okay, so that's why I said this takes a little bit of reasoning. Store the bit pattern found in register 2. The contents of register 2 is 11, whose address is, okay, store the bit pattern found in register R in the memory cell whose address is, okay, so we're going to take, okay, so the contents of R. So the memory cell 0, 2, so what that, I interpret that is, so whose address is XY. So 0, 2 equals 0 hex 11. That's the answer. Sorry about that. Again, that's why I said you got to read this a few times to fully understand some of them. Some of them are just, the descriptions are a little poorly written if you ask me. So store the bit pattern found in register in the memory cell whose address is XY. So at memory 2, it's hex 11. So if you go back up here, now they changed this. This is going to be, right? See, so they changed that. They changed it to 11. Okay. Then we have this last instruction, 3. And that's an easy one. That is, 0, 0. Now, if you look this up in the book, that's a halt, halt instruction. Okay. So now, what was the question in the homework? We went through the machine cycle. We did that. Okay. Assuming that program initially contained record the contents of the program instruction memory cell address 2 at each phase of the stage. That's why they're asking you that at the memory at 2, because as you could see when I went through this, on the second step, we changed it to 11, hex 11. It was originally hex 32. It's hex 11. Okay. So I don't know the folks on the call. Did you understand how you chime in? Did you understand how I did that? You can shout out yes, no.
I'm kind of confused on how you got 0x11 because I thought the XY was 02.
Okay, so that's for step 2. So step 1, we have register 2 equals hex 11, right? So that's the pattern, that's the register 2. So this other step was 03, store the bit pattern found in R. Let's take this out. Let's take this part out. Okay, that's just store the bit pattern found in register R. So register R is 2, right? So we're dealing with register 2. Store the bit pattern found in register 2. What's the bit pattern found in register 2? Right here, right? We calculated that from the previous step. Did you understand this previous step?
Yeah, I was tracking the previous step.
Okay, so we from the previous step we calculated that R equals hex 11, right? So store the bit pattern found in register R in the memory cell whose address is XY. So that's why then uh, memory XY, that's XY equals uh, XY equals 0, 2, right? So it's a little the English the description here is a little weird. Store the bit pattern found in register R, which we know is hex 11, right? 1 1. In the memory cell whose address is XY. XY is 2. It's the memory cell X2. So therefore at memory X2 and memory 2, the bit pattern equals 11, right? So what they did is they just changed this here. Through this instruction, they changed this. So they loaded it into a register. The first step, it was loaded into a register. Like we said, right? You take values, you load it into a register. They load it into a register, and then what they did is they took what was in the register and they put it in a memory location too,
Okay, that makes
right?
sense now.
Okay, yeah. It was just,
Thank you.
if I was to rewrite this, here would be a good one, right? Store, like, store in memory address XY. I spelled that wrong. XY. Store memory address XY. What is in register? What is in register R, right? If they had said that in their description, then this would have been much easier. It's their description, it's terrible, right? Then that would be so straightforward. That's what they're saying there. So did that help?
Yeah.
So
Yeah, the
hopefully that
wording makes
helps.
it make way
Yeah,
more
it's
sense
the
with
word.
this
So
one.
feel free that if you read it and if it makes more sense to you to reword it to what you understand. Okay. So let's go back here. So no, 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 no. So that covers that problem. Suppose that hard disk, so that you guys got that from the first homework, number five. You can do that, I'm sure. Suppose the memory cells addresses at these addresses all contain the following bit
Hello, Professor.
patterns. Yes. Hello?
Um, I I I have a question
Sure.
concerning that problem. At instruction two, we were using 0x302. I was wondering where the two are, where we got it from, because that wasn't part
I'm
of the.
sorry, you're very choppy on my end.
Oh, okay. Can you hear me?
Now I can hear you much better.
Okay, so I was wondering, right, at the instruction two, we were we were using 0x3 02. So I was wondering where the 2R came from, the register.
Well, okay, so again, if you take this, if you take this, right, this is what you can do, right? So you know the first part, right? You can do this. Sorry. Hopefully this explains it. Uh, what- okay, so you separate the amount. Okay, so you know it's 3, x3, right? So now if you come here to 3, if you notice 3 is RXY, right? See that right here, the operand, opcode and operand. I get confused between the words. So the
Yeah,
opcode is 03 and the operand is RXY. So if you come back in here, like I said, if you split this out, all you do under here is put RXY. R stands for register. I like to put spaces after it. X and then Y. Okay. So now we have the register X and Y. So now all we have to do now is follow the description of what that all means, right? So, no, 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 no. Uh, Here, I get come to you. So, right here, store the bit pattern found in register R as the memory cell's address XY. So that's what I did. I copied that in here, copied the description, right? So here it is, a little space. So store the bit pattern found in register R. That's register 2 in the memory cell whose address is store the bit pattern found in register R in the so bit pattern register is register 2. We calculated that up here in the previous step, right? That was hex 11. The bit pattern
yeah,
was 1 1. And so now what it's saying is in the memory address XY, XY is 2. So you're taking a 1 1 and storing it in 0 2, which is happens to be our memory location up here, right? So I just put that here. So it's kind of weird. You have to admit that this question is a little weird because I'm changing the memory location with my instruction set. So that's a little unusual. I have to admit to you that one. It's an unusual. Um, I don't think this usually happens. But did it make sense how I explained that?
yes, yes, it does. Thank you.
Okay, good. I know my little confusing when I started. I was see show you I was confused myself. I had to look at it a few times. Like, oh, wait a second. So okay, so uh, because I know people have problems with this problem, I know just help, just try to get the first one done, and then so this is just a larger one of them. Okay, so you do the same thing, split them up in groups of two. Try to interpret the opcodes and the operands, copy and paste like I'm showing you, substitute to RXY or whatever else is there, RST, and just follow what it's doing, okay? And try to answer these questions. If you get if you get number 4, understand that, then I think number 6 will be I'm not saying it's going to be easy, but it's not going to it's you'll have a good idea. And it's important to show all your work, okay? Because You may answer the questions wrong, but I want to see your work because I can give you partial credit on this, okay? So it's very important to do like what I was doing. Show it step by step, document it, show the operand, opcode, put in the description, assign it what you think they are, right? So that goes a long way to me because honestly, I'm not sure if I'm concerned about the absolute answer. I know it's going to sound crazy. I'm really more concerned that you're following the machine cycle, okay? And that you understand it's a 16-bit or a 2-byte machine and that you're splitting up the addresses properly. Because we all make mistakes interpreting some descriptions, right? And you see how I had a problem. I looked at it in the beginning. I was like, oh, wait a second, this isn't right, right? So show your work on this, okay? Do not use ChatGPT for these for 4 and 6. Do not use ChatGPT, okay? Because I'm not sure if ChatGPT or any LLM will do it properly. Because I'm not sure if it knows the vol machine. How good is it knowing the vol? I haven't tried that lately. So I would not use it. I make sure you don't do it. Now, of course, for this number 5, if you want to use ChatGPT and just get your answer, do it like you did the first time, like that's fine. So that's why I say so far I've covered 4, 5, 6. So in each of the following cases, write a short program in vol. Okay, so write a program. Okay, so what becomes very interesting about this is writing a short program. We all get confused because in the presentation we showed a Python program. And then now we showed machine code, right? And so forth. So I think this is a poorly worded question. And I did not have the chance to change it, be honest with you. But it says the program. It says the program. Uh, so what I want to go up here is what is a Deval architecture. Let's go back up to here. So we're on chapter 2, real quick, right? So I want to say, what is the book saying is a program? I always wondered every semester, and we're going to go through it right now because I accepted multiple ways to do this for number 2. Let's see. I want to just bear with me on this one. Okay. Uh, Get to do. I don't like this. I can't get. I don't have. Chapter 1. It's a PDF. Chapter review problems. Okay. Yada, yada, yada. Okay. Social issues. Chapter 2, computer architecture, rhythmic communicating with other. Is there something in the book that says what is the book considering a program? Programming data manipulation. Okay, so that's well let's see. Maybe can I search for program from here? Is there a find? Do you know? Or maybe I right click, do a find. No. So let's just go through this quickly. Wait, data manipulation, okay. Computer architecture, we covered that. The stored program concept, okay. The instruction repertoire, the list of machine instructions that typically might be to decode and execute. That one machine, okay. Data transfer, okay. Rhythmic logic, a machine language. See, they deal mostly with we're dealing with the machine language, right? And there's the machine code. I want to see when we get to the program, an execution of program execution. Okay. What is it considering a program? Because I'm confused on that myself, be honest with you, this question. There's the logic that was review. Rotation shift operators, okay, rhythmic operations. Just hold on a minute. Off controllers. So the folks on the call, what's your opinion of when they ask for a program? Should that be the machine code, or can that be a Python program, or what do you think? Does anybody have an opinion on this one? Programming data. One of the essential features of computer programs such as Python. See, they talk about Python.
I don't like what I'm
So
gonna say. I don't like what I'm gonna say here, Professor, but I think they mean the machine code, like the assembly code or
that,
whatever for Vol.
that's what I think. I think so because I've had folks in the past uh, provide at a much higher level and actually provide me the Python program because it's confusing. They should have said machine code. So, so how about this? Provide me the machine code uh, for that question. I think that'd be better since we're working on that. If you really rather do a Python programs to do them, you can do that too. I'll probably accept both because of the way the question's worded. Uh, I don't think it's so it needs you to write a short program involved. Okay, it says a program involved, which I think involved. What they really mean is give me the machine code because that's why they're saying involved. If it was just a program, it would say write me a program. It wouldn't matter if it was involved, right? Because we talked about the higher level language. So for number seven, give me the machine code, okay, for that. And so basically, what you have to do again is you have to use this. Well, you have to use the Appendix C with the opcodes and the operands, and you have to figure them out. Okay? Do you think that's fair? Right? So here's the simple machine language. So use these opcodes and operands to answer that question. So, that may be a little more challenging. That may take you some time to figure out. I know it will. It's probably the first question is kind of easy, I think, but I can tell you the B and the C will take you probably have to try it one day, look at it the next day, and then maybe the following day, and you'll figure it out. Okay, so that may take you a couple days, not like 8 hours, not like a long time each day, but that's how I'd approach it. I would first take a first stab at it, think about it, review it, and then do it again. Go over it a few times. Okay, and so it's worth 70 points, and like I said, show all your work so I can give you some partial credit if it's not 100% correct. If you just put the answers in and I don't think they're right, you're not going to get any credit at all. Uh, so that's all I have for tonight. Like I said, if you can get by this homework, I think you're going to find the other lectures much more enjoyable. I think what is the next one? The next uh, the next topic. Oh, the next topic is database systems. Everybody loves that one, and everybody gets an A on that one. Okay, it's just you write a bunch of SQL statements, SQL, uh, against the database. But we do have to be able to access the database. I will cover that in the lecture as well. It's a little tricky how to upload the data. We're using Oracle Online Database. Okay, so okay, I want to hope everyone has a great week. Hopefully you enjoy the assignment. You got any questions? Concerns, struggle with something, need something explained further, drop me an email, text me, whatever, and I'll try to help you. Um, hopefully everyone has a great week, and I guess every other week we'll meet again in 2 weeks. Take care.
Thanks, Professor. Have a good night.
Good night.
Thank you, sir.
Yep, take care.
Professor.
Yes.
I'm so sorry. I had network problems, but I'm back now. I I was wondering, what book did you use to get the operand and the description? I didn't
I'm
see it in the
sorry,
textbook.
you're so very choppy. I don't know. I don't know.
Okay.
It's my end. Okay.
Um, I said I'm so sorry. I had traffic issues with my ISP, but I'm back now. So I was just wondering, what book did you use to get the operand and those descriptions? Because I
Oh,
didn't
okay.
find
Let
them
me
in the
share my
textbook.
screen. I'm glad you asked me. Let me share my screen again. So the textbook, okay, the textbook here is in the reading material, and I downloaded it from here. I downloaded the 13th edition. Okay. Hopefully this answers your question. And then from there, I opened it. And then, of course, you have all the chapters in here. And then to get that chart, I went more towards the, of course, I don't think, uh, you see, it's a pain in the neck when it's a PDF because you don't get links. Is there a link? Oh, it is. I was wrong. Okay, so let me do this. I feel kind of silly. So it's in the appendix. It's the appendix. Anyway, had a vol, a simple machine language. I went here to Appendix C. Here they talk about the vol architecture, the vol machine language, and then here's the operands and the
Oh,
opcodes. And that's what I used.
okay.
And that's what you'll have to use.
Okay. Okay.
Okay?
Thank you. Thank you.
Oh, you're
Yeah.
welcome. Any questions? I'm glad you're asking these questions now instead of we're trying to beat your head against the wall for a week and not getting anything accomplished. So thank you for the question. Anybody else have any other questions before I end the lecture? If not, okay, good night to the folks who are on, and we'll see each other in 2 weeks. Take care.
Thank you, Professor. Good night.
Yeah, good night.